In 1924, two Polish mathematicians published a proof that you can take a solid ball, cut it into 5 pieces, and reassemble those 5 pieces into 2 solid balls, each identical in size to the original. Not larger, not smaller. Identical, same volume, same radius. 2 perfect copies from one original, using nothing but rotations and translations. No stretching, no adding material, just cutting and rearranging. That is not a thought experiment. That is not a conjecture, waiting to be proven or disproven. That is a theorem, published in Fundamenta Mathematicae, Volume 6, pages 244 through 277. It has been verified, studied, extended, and taught in graduate mathematics programs for a century. It is called the Banach-Tarski paradox, and every working mathematician accepts it as true. And here is the part that should keep you up tonight. Physics says this is impossible. Conservation of mass says you cannot create matter from nothing. Conservation of energy says you cannot double the energy content of a system through rearrangement. Every experiment ever conducted, every measurement ever taken, every physical law ever formulated says that if you start with one ball, you end with one ball. You do not get to conjure a second one out of geometry. Both of these are correct. The math is airtight. The physics is airtight. They directly contradict each other, and neither one has a flaw. I spent a genuinely unreasonable amount of time researching this, weeks, and the further I went, the worse it got. Because this is not a quirky math puzzle. This is not some abstract curiosity that lives safely inside a textbook. What this paradox reveals, once you actually follow it all the way down, is something so uncomfortable about the relationship between mathematics and reality that I am honestly not sure the full implications have been absorbed by anyone, including the people who proved it. What nobody knew in 1924, what Banach and Tarski themselves did not fully appreciate, was that their proof depended entirely on a single axiom, one rule, one assumption baked into the foundation of mathematics. And that axiom, the thing holding the entire paradox together, would later be proven to be undecidable. You cannot prove it true. You cannot prove it false. It exists in a state of permanent logical limbo, and virtually all of modern mathematics is built on top of it. Think about what that means for a second. Every equation in physics, every model in engineering, every calculation that keeps bridges standing, and planes flying, and GPS satellites synchronized to 11 decimal places of accuracy. All of it rests on a mathematical framework that includes, as a proven consequence, the ability to double a solid object by cutting it into 5 pieces. The tool we use to describe reality contains a result that reality explicitly forbids, and the axiom responsible for it cannot be verified. You were never told this, and I think the reason you were never told this is that the implications are genuinely difficult for the scientific establishment to talk about publicly without sounding like they have lost their minds. But I am going to walk you through the entire thing. The proof, the axiom, the century-long war over whether to accept it. The mathematicians who tried to stop it and were destroyed for trying. The alternative mathematical universe where the paradox does not exist, and the question that sits underneath all of it, the one that nobody, not one person alive, has been able to answer. If mathematics can prove something that physics says is impossible, and both proofs are valid, what does that tell you about what mathematics actually is? Is it describing reality, or is it describing something else entirely? something larger than reality, and we have been assuming the two are the same thing without ever checking. That question has no answer. Not yet. Possibly not ever. And by the time we are done here, you will understand why. Let me start with the man who proved it, because his life is in some ways more impossible than his theorem. Krakow, 1892. Stefan Banach was born on March 30th at St. Lazarus General Hospital, and the circumstances of his birth read like something out of a Dickens novel, if Dickens had a cruelty streak. His father, Stefan Grecek, was a private in the Austro-Hungarian army. Military regulations prohibited soldiers of his rank from marrying. His mother, listed on the baptism certificate as Katarzyna Banach, appeared at the hospital, gave birth, attended the baptism on April 3rd, and vanished. Banach never learned who she really was. His father had been, according to the family, sworn to secrecy. Banach spent his entire life unable to discover his own mother's identity. He was handed off to Francesca Brouwer, a laundress, who raised him in Krakow. His early intellectual life was shaped by Julius Mene, a French émigré who taught him the French language and, more importantly, noticed that the boy was extraordinary. Banach was largely self-taught in mathematics. He attended the Jagiellonian University briefly, but there is no record of him completing a degree in the traditional sense. He was, by any institutional measure, nobody. And then, one evening, in 1916, something happened in a public park that would change the course of mathematics permanently. Hugo Steinhaus, already an established mathematician, was taking a walk through the Planty Gardens in Krakow. This was the park that rings the old city centre, popular with students and professors and anyone looking for fresh air in a city that did not have much of it. Steinhaus overheard two young men sitting on a bench. They were discussing Lebesgue integrals. Now, you need to understand what Lebesgue integrals were in 1916. This was not something you discussed casually. This was cutting-edge measure theory, the kind of mathematics that was barely taught in the most advanced university seminars in Europe. Hearing two random young men in a public park throwing around Lebesgue integration was roughly equivalent to overhearing strangers at a coffee shop debating the finer points of quantum chromodynamics. It simply did not happen. Steinhaus approached them. One was Otto Nikodym, who would go on to have a distinguished career. The other was Stefan Banach. Steinhaus posed a problem he had been working on. A few days later, Banach came back with a solution. Their first joint paper was published in 1918. Steinhaus would later describe Banach as his greatest mathematical discovery. He was not joking. A commemorative bench was placed in the Planty Gardens in 2016 on the centenary of the encounter. Banach never went through a traditional doctoral process, but his 1920 doctoral thesis defined what we now call Banach spaces, and it essentially invented functional analysis. The man with no degree, raised by a laundress, overheard in a park, created an entire branch of mathematics. And then, in 1924, he and Alfred Tarski published the theorem that proved you can turn one sphere into two. I personally think Banach's story is the most underrated origin myth in all of science. We hear endlessly about Einstein at the patent office. We hear about Ramanujan and Hardy. But a self-taught orphan overheard discussing measure theory on a park bench, who then went on to co-author one of the most disturbing results in the history of mathematics. That story deserves to be known And the reason it is not, I think, is because the result itself makes people so uncomfortable that they would rather not think about the person who produced it. His co-author had his own impossible story. Alfred Tarski was born Alfred Teitelbaum in Warsaw on January 14, 1901, to a secular Jewish family. In 1923, he changed his surname, inventing Tarski from nothing because, as he later explained, it sounded Polish, was simple to spell, and was unused. He also converted to Roman Catholicism, despite being an avowed atheist. The reason was not spiritual. The reason was that Poland in the 1920s was a country where being Jewish meant your academic career could be destroyed before it started. In 1937, a university chair in Poznan was abolished entirely, rather than be given to a Jewish candidate. Tarski understood the mathematics of survival as well as anyone, and he needed that understanding because his escape from Poland has the texture of a thriller. On August 11, 1939, Tarski boarded the SS Pilsudski in Gdynia. It was the last ship to leave Poland for the United States before the German invasion on September 1st. He carried a small suitcase, summer clothing, and enough money for a few weeks. His wife Maria and their children Jan and Ina stayed behind in Warsaw. He did not see them again for 7 years. Nearly all of his extended family were murdered in the Holocaust, and the ship he sailed on, the Pilsudski, was torpedoed and sunk on its return voyage. He escaped on a vessel that ceased to exist almost immediately after delivering him. So those are the two men, a self-taught orphan and a man who invented his own identity to survive. And together, in 1924, they proved that geometry contains a secret so strange that physics cannot accommodate it. But the proof itself is where this story really starts to become disturbing. Because the way it works is not complicated in the sense of being hard to follow. It is complicated in the sense that each step is individually reasonable, and the conclusion is individually insane. And there is no point where you can say that is the step where it goes wrong. It never goes wrong. It just arrives somewhere impossible. Here is how you double a sphere. The proof has 4 steps, and each one builds on the last like floors of a building that should not be able to stand. The first step has nothing to do with geometry. It is pure algebra, and it starts with something called a free group. Take 2 symbols, call them A and B. Now consider every possible finite string you can make from A, B, and their inverses. So A, B, ab, ba, abba, abba, bab, and so on, going forever. Remove any cancellations, meaning if A appears next to its inverse, they disappear. Same for B. What you are left with is called the free group on 2 generators, and mathematicians denote it F2. This group has a property that when you first encounter it, seems like a parlor trick, but turns out to be the engine of the entire paradox. You can partition the non-identity elements of this group into 4 sets. Words that start with A, words that start with A inverse, words that start with B, words that start with B inverse. 4 buckets. Everything goes into exactly 1 bucket. Now here is the trick. Take the bucket of words starting with A and multiply every word in it on the left by A inverse. What happens is that the A at the front cancels, and you get back every possible word, including words that start with B, B inverse, and A inverse. You get the entire group back from 1 bucket. Do the same with the A inverse bucket. multiplying by A, and again, you recover the entire group. The group contains 2 copies of itself, 4 pieces, reassembled into 2 complete copies using nothing but the group operation. And no, I am not making that up. This is standard group theory. You can verify it yourself with a pencil and paper in about 15 minutes. But here is the thing. So far, this is just algebra, letters and symbols. It has no geometric content. It does not describe physical space. It describes an abstract algebraic structure. Step 2 is where the algebra meets geometry. And this is where it gets uncomfortable. In 3-dimensional space, you can find 2 specific rotations that generate a free group. Pick a rotation around the x-axis by the angle whose cosine is 1/3. Call it rotation A. Pick a rotation around the z-axis by the same angle. Call it rotation B. Compose them in all possible combinations. Banach and Tarski proved, and this has been verified many times since, that these 2 rotations and their inverses, when composed in all possible finite sequences, generate a subgroup of the rotation group SO3 that is isomorphic to the free group F2. The algebraic paradox maps directly onto rotations of 3-dimensional space. I want to be very specific about what isomorphic means here, because it matters. It means the algebraic structure of the free group is perfectly preserved. Every relationship, every cancellation, every property that made the free group paradoxical carries over exactly into the world of rotations. The abstract trick with letters becomes a concrete trick with spatial rotations. The algebra is the geometry. And this is where people usually ask the obvious question: why 3 dimensions? Why not 2? The answer is one of those facts that is simple to state and profoundly unsettling in its implications. The rotation group in 2 dimensions, so too, is abelian. That means all plane rotations commute. If you rotate a disk 30 degrees and then 45 degrees, you get the same result as rotating 45 degrees and then 30 degrees. Order does not matter. And because order does not matter, you cannot generate a free group. The free group depends on non-commutativity. It depends on the fact that Abe is different from BA. In 2 dimensions, that never happens. In 3 dimensions, rotations do not commute. Rotate a ball around the x-axis and then the z-axis, and you get a different result from rotating around the z-axis first and then the x-axis. 3-dimensional space has enough structure, enough complexity, enough room for rotations to disagree with each other that a free group can form inside it. You live in 3 dimensions, and 3 dimensions are exactly the ones where the paradox becomes possible. That is not a coincidence. That is a fact about the geometry of the space you occupy. Step 3 is where things go from unsettling to genuinely alien. You have a free group living inside the rotations of 3-dimensional space. That free group can be paradoxically decomposed, as we showed in step 1. Now you need to transfer that decomposition from the group to the actual sphere. The rotations act on the unit sphere. Every point on the sphere gets moved to another point by each rotation. You can organize the points of the sphere into orbits, groups of points that are connected to each other by the rotations in our free subgroup. There are uncountably many of these orbits, and to decompose the sphere, you need to select exactly one representative point from each orbit. This is where the axiom of choice enters, and it does not tiptoe in. It kicks the door down. The axiom of choice says that, for any collection of non-empty sets, there exists a function that selects exactly one element from each set. It sounds almost trivially obvious when you say it that way. If you have a bunch of non-empty boxes, you can pick one item from each box. Of course you can. How could you not? But the orbits on the sphere are uncountably infinite. There are more of them than there are natural numbers, more than there are rational numbers, more than there are decimal expansions you could ever write down. And the axiom of choice says you can make a selection from every single one of them, simultaneously, without providing any rule or method or algorithm for how the selection is made. It asserts that the completed selection exists without ever specifying what it looks like. You cannot write it down, you cannot compute it, you cannot describe it, you can only assert that it is there. Once you have those representatives, you use the paradoxical decomposition of the free group to decompose the sphere into pieces. The free group's 4 into 2 trick becomes a 4 into 2 trick on the sphere itself, minus a countable set of fixed points that get absorbed by a separate rotation argument. The sphere is split into pieces that, when rotated, reassemble into 2 complete spheres. Step 4 extends the result from the sphere's surface to the solid ball by connecting each surface point to the center with a line segment, then handling the center point with another rotation trick. And that is it. One sphere becomes 2. Proven, published, accepted. But the result has a corollary that is even more disturbing than the theorem itself. And it is the corollary that Banach and Tarski actually emphasized in their paper. It is called the Strom form. Any 2 bounded subsets of 3-dimensional space with non-empty interiors are equi-decomposable. Any bounded solid shape can be cut into finitely many pieces and reassembled into any other bounded solid shape. A sphere can become a cube. A cube can become an icosahedron. And a single P, can be cut into finitely many pieces and reassembled into a solid ball the size of the sun. That is sometimes called the P and the sun theorem. It sounds like a joke. It is not a joke. It is a proven consequence of the same axioms that underpin all of modern mathematics. And the thing is, the paradox did not appear from nowhere. It had a precursor, and the precursor's story carries its own terrible weight. In 1914, Felix Hausdorff published a paper in Mathematische Annalen, volume 75, pages 428 through 433, titled Bemerkung über den Inhalt von Punktmengen. In that paper, Hausdorff proved that the surface of a sphere can be partitioned into 4 sets, 3 of them congruent to each other via rotations, with the 4th being a countable set of scattered points. And the 3 congruent sets have the property that one of them is also congruent to the union of the other 2. This is paradoxical for the same reason Banach-Tarski is. If any rotation invariant measure existed on all subsets of the sphere, you would get contradictory values. Hausdorff's technique was essentially the same. 2 rotations generating a free group, orbit representatives selected via the axiom of choice, the algebraic paradox transferred to the sphere. What Banach and Tarski added 10 years later was the elimination of the countable exceptional set, the extension from the sphere surface to the solid ball, and the devastating strong form. Hausdorff himself had one of the most tragic endings in the entire history of mathematics. He was Jewish, and when the Nazi regime came to power, he was stripped of his position at the University of Bonn. In January of 1942, facing imminent deportation to a concentration camp Felix Hausdorff, his wife Charlotte, and her sister Edith Pappenheim took lethal doses of veronal. In a farewell letter to a friend, Hausdorff wrote that he was sorry to cause difficulties. The man who first showed that the sphere contains a paradox chose to leave a world that had become one. So the genealogy of the paradox runs from Hausdorff in 1914 through Banach-Tarski in 1924, and both the theorem and its precursor are soaked in the catastrophes of 20th century Europe. The mathematicians, many of them did not, but you caught the critical detail, right? The axiom of choice. That selection from uncountably many orbits, the one that cannot be computed or described or written down. That selection determines what the pieces look like, and the pieces look like nothing you have ever imagined. They are called non-measurable sets. And this is where most popular explanations of Banach-Tarski stop, because what comes next is hard to convey. The pieces do not have volume. That is not a metaphor. It is not that they have a very small volume, or a volume that is hard to calculate, or a volume that rounds to zero. The concept of volume does not apply to them. They are outside the domain of Lebesgue measure entirely. Henri Lebesgue formalized measure theory in 1901 and 1902, creating the system we use to assign lengths, areas, and volumes to sets of points. His measure is countably additive, meaning if you chop a region into countably many non-overlapping pieces, the total measure equals the sum of the individual measures. It is translation invariant and rotation invariant. It assigns the unit cube a volume of 1, and it works beautifully for every set you are ever likely to encounter in the physical world. But in 1905, just 3 years after Lebesgue published his theory, an Italian mathematician named Giuseppe Vitali showed that Lebesgue's system has a hole in it. Vitali constructed the first non-measurable set, and his construction is elegant and devastating in equal measure. Here is how it works. Take the real numbers between 0 and 1. Define a relation. Two numbers are equivalent if their difference is rational. This partitions the interval into uncountably many equivalence classes. Each class contains numbers that differ from each other by rational amounts. Now, using the axiom of choice, select exactly one representative from each class. Call the resulting set V. This is the Vitali set. Now consider all the rational numbers between -1 and 1. There are countably many of them. Translate the Vitali set by each of these rational numbers. The resulting countably many translated copies of V are pairwise disjoint, meaning no two of them overlap, and their union contains the entire interval from 0 to 1, while being contained inside the interval from -1 to 2. If V had a positive Lebesgue measure, then the countable union of translated copies would have infinite measure, since countably many copies of a positive number sum to infinity. But the union is contained in an interval of length 3, so its measure is at most 3. Contradiction. If V had 0 measure, then the union would also have 0 measure, but it contains the interval from 0 to 1, which has measure 1. Contradiction. The only possibility is that V is not Lebesgue measurable at all. The system cannot assign it a number, and the entire construction depends on exactly one step: the use of the axiom of choice to select representatives from uncountably many equivalence classes. The pieces in the Banach-Tarski decomposition are non-measurable in the same way, for the same reason. They are constructed via the axiom of choice, and their structure is so pathological that the concept of volume cannot be applied to them. And here is the part that I think is genuinely the most underrated aspect of this entire story. The theorem does not just say you can double a ball. The theorem proves something much more concrete and much more disturbing. It proves that there is no finitely additive rotation invariant measure defined on all subsets of three-dimensional space that gives the unit cube a volume of 1. That is not a statement about abstract mathematics. That is a statement about the structure of the space you are sitting in right now. Three-dimensional space, according to this theorem, cannot be measured consistently if you insist on measuring everything. Some subsets of the space you occupy are, in a precise mathematical sense, beyond measurement. There is a common misconception that Banach-Tarski is just an abstract curiosity, a weird math trick with no real consequences. I have seen this dismissal in popular science writing, in Wikipedia talk pages, in Reddit threads, and I want to be very direct about this. That dismissal is wrong. The theorem has concrete, specific, verified consequences for the theory of measurement in three-dimensional space. It is telling you something about where you live. But if the pieces have no volume, and the entire proof depends on a single axiom that lets you make selections without a rule, without a procedure, without any constructive method at all, then the obvious question becomes, is that axiom true? Is the axiom of choice a description of mathematical reality, or is it something mathematicians decided to believe because it was useful? Because it turns out that question has an answer. And the answer is the most disturbing thing I have ever learned about the foundations of human knowledge. The axiom of choice was born on September 24th, 1904, in a 3-page letter from Ernst Zermelo to David Hilbert, published in Mathematician, volume 59, pages 514 through 516, and the storm it created has not stopped in over 120 years. To understand why this tiny axiom caused such fury, you need to understand what it actually says. The axiom of choice states that for any collection of non-empty sets, there exists a function that selects exactly one element from each set. That is the entire axiom, one sentence. And on its face, it seems almost insultingly obvious. If you have 3 boxes, each containing some objects, you can pick one object from each box. Of course you can. Your hand reaches in, your fingers close around something, you pull it out. Done. If you have 100 boxes, same thing. 1,000, 1,000,000. Your arm would get tired, but the principle is not in question. But what if you have infinitely many boxes? And not just countably infinitely many, not just one for each natural number, but uncountably infinitely many. More boxes than there are integers, more boxes than there are fractions, more boxes than there are decimal numbers you could ever write down in the remaining lifespan of the universe. And what if the objects in each box are not labeled, not ordered, not distinguishable by any property you could ever name or compute? The axiom of choice says you can still pick one from each. Not that you could do it if you had infinite time. Not that a procedure exists that would eventually finish. It says the completed selection exists right now as a mathematical object. The function that maps each box to a chosen element is real. It is there. It is just that nobody can tell you what it looks like, or how to compute it, or what rule governs it. It exists without being constructible. Zermelo introduced this axiom because he needed it to prove the well-ordering theorem, which says that every set can be equipped with a well-ordering, a total order, where every non-empty subset has a least element. The natural numbers are naturally well ordered. The rational numbers are not in their usual ordering, but Zermelo's theorem says you can rearrange them so they are. The real numbers, same thing. You can well order the real numbers. You cannot write down what that well ordering looks like. You cannot describe it. You cannot compute it. But it exists. The axiom of choice guarantees it. The backlash was immediate, and it came not from cranks or amateurs, but from some of the greatest mathematicians in France. In 1905, 4 mathematicians exchanged a series of letters that were published in the Bulletin de la Société Mathématique de France, volume 33, pages 261 through 273. The letters are collectively known as the 5 letters, the 5 letters on set theory, and they represent the most famous philosophical dispute in modern mathematics. The participants were Jacques Hadamard, Émile Borel, René Baer, and Henri Lebesgue. Hadamard defended Zermelo, and he was alone. He argued that the objection to the axiom of choice was purely psychological, that it reflected human limitations rather than mathematical truth. The other 3 disagreed, and they disagreed ferociously. Lebesgue posed what I think is still the sharpest challenge anyone has ever raised against the axiom. He pointed out that making infinitely many choices cannot mean writing down or naming the chosen elements one by one. Life is too short for that. So what does it mean to say you have made the choices? If you cannot describe the result, if you cannot exhibit it, if you cannot compute it, in what sense does it exist? Lebesgue was not asking a rhetorical question. He was asking a foundational one. What does existence mean in mathematics? Borel accepted the axiom for countably many sets, but rejected it for uncountably many. He was willing to make infinitely many choices as long as the infinity was small enough. Once you crossed into uncountable territory, he drew the line. Baer went further, questioning whether infinite sets placed mathematics entirely in the realm of potentiality rather than actuality. And here is the part that makes this story truly ironic, the detail that historians of mathematics love to point out with barely concealed glee. Gregory H. Moore documented in his 1982 book, Zermelo's Axiom of Choice, that Baer, Borel, and Lebesgue had all used the axiom of choice implicitly in their own published research. They had made uncountably many arbitrary selections in the course of proving their own theorems without noticing. They had used the countable union theorem, which itself depends on a form of the axiom. They were arguing against a principle that their own work depended on. The axiom of choice was already inside the house before anyone thought to lock the door. I actually think this is the funniest thing in the entire history of mathematics. 3 of the most rigorous mathematicians who ever lived attacking an axiom on philosophical grounds, while their own theorems quietly relied on it. It is the mathematical equivalent of protesting fossil fuels while filling up your car with gas. And it reveals something important about the axiom. It is so natural, so automatic, so deeply embedded in mathematical reasoning that even its opponents could not avoid using it. But here is where it gets worse. If the axiom of choice were simply controversial, that would be manageable. Controversies resolve. Evidence accumulates. One side wins. But what happened with the axiom of choice is something far stranger. It did not get resolved. It was proven to be unresolvable. 1938. Kurt Gödel, working in Vienna and then at the Institute for Advanced Study in Princeton, proved that if the standard axioms of set theory the ZF axioms are consistent, then adding the axiom of choice does not create a contradiction. The technical achievement was the construction of the constructible universe, denoted L, a model of set theory built by transfinite recursion, where every set is definable from earlier sets. In this model, everything is so well structured that the axiom of choice holds automatically. No contradictions arise. His initial announcement was a short note in the Proceedings of the National Academy of Sciences, Volume 24, pages 556 through 557. The full treatment came in his 1940 monograph, The Consistency of the Continuum Hypothesis. What Gödel proved was this: if the other axioms do not already produce a contradiction, then adding the axiom of choice will not produce one either. You can safely accept AC. It will not break mathematics. 25 years later, everything changed again. 1963. Paul Cohen, a mathematician at Stanford, proved the opposite direction using a technique he invented called forcing. Cohen showed that you can also safely deny the axiom of choice. If the ZF axioms are consistent, then adding the negation of AC does not create a contradiction either. You can reject the axiom and mathematics still works. His papers appeared in the Proceedings of the National Academy of Sciences, Volume 50, pages 1143 through 1148, and Volume 51, pages 105 through 110. Together, Godel and Cohen established something that I think is genuinely one of the most important facts in the history of human thought, and it receives almost zero public attention. The axiom of choice is independent of the other axioms of set theory. It cannot be proved from them. It cannot be disproved from them. It floats free, like Euclid's parallel postulate. You are free to accept it or reject it. Both options produce consistent mathematics, but they produce different mathematics with different truths. The parallel to Euclid is almost exact, and it deserves a moment. For over 2,000 years, mathematicians tried to prove Euclid's fifth postulate, the parallel postulate, from the other four. They failed. In the 19th century, Bolyai, Lobachevsky, and Riemann showed why. The parallel postulate is independent of the other axioms. You can accept it and get Euclidean geometry. You can deny it and get hyperbolic or elliptic geometry. All three geometries are internally consistent. None is more true than the others in any mathematical sense. And crucially, it turned out that physical space-time is not Euclidean. General relativity describes a curved space-time that is locally Lorentzian, and the parallel postulate fails in the presence of gravity. The natural geometry, the one that matches reality, was not the one mathematicians had assumed for millennia. The situation with the axiom of choice is analogous. Accept it and you get ZFC mathematics with Banach-Tarski. Deny it and you get ZF mathematics, or the Solovay model, without the paradox. Both are consistent, and nobody knows which one describes the physical universe. Nobody knows whether there even is a fact of the matter. I need you to really sit with that for a moment. Mathematics, the thing we treat as the bedrock of certainty, the foundation of physics, the language in which we write the laws of the universe, contains a fundamental axiom whose truth value cannot be determined. You can take it or leave it. If you take it, you get the Banach-Tarski paradox. If you leave it, you lose the Banach-Tarski paradox, but you also lose an enormous amount of mathematics that you probably want to keep. Without the axiom of choice, Tychonoff's theorem fails. That is the theorem that says an arbitrary product of compact spaces is compact. It is equivalent to AC, meaning it is exactly as strong as the axiom of choice itself. Without AC, you cannot guarantee that every vector space has a basis. Without it, the Hahn-Banach theorem, one of the cornerstones of functional analysis, the very field that Banach himself created, does not hold. Without it, Zorn's lemma, which is used constantly in algebra and topology, disappears. Without it, you cannot even prove that every infinite set has a countable subset. In some models of ZF without the axiom of choice, the real numbers become a countable union of countable sets, which devastates the very measure theory and analysis that Lebesgue and Borel built their careers on. So, the choice, if you will, forgive the pun, is not between a clean mathematics and a dirty one. It is between a mathematics that is rich, powerful, and includes proven impossibilities, and a mathematics that is impoverished, restricted, and loses results that working mathematicians use every single day. That is the trade. That is the actual situation. And mathematicians chose the rich version, the one with the paradox, the one with the undecidable axiom, because the alternative was too costly to accept. This decision seemed small at the time. It was not. Paul Cohen deserves a moment here because his story is almost as improbable as Banach's. He was born in 1934 in Long Branch, New Jersey, and grew up in Brooklyn, the son of Polish Jewish immigrants. His mother took him to the New York Public Library when he was 9 years old and checked out a book on calculus for him. He graduated from Stuyvesant High School at 16. He earned his PhD under Antoni Zygmunt at the University of Chicago, and his thesis was in harmonic analysis. He was, by any measure, an outsider to set theory and mathematical logic. He wandered into the field because he found the problems interesting, invented a technique that nobody had imagined was possible, solved half of Hilbert's first problem, and received the Fields Medal in 1966. It remains, to this day, the only Fields Medal ever awarded for work in mathematical logic. Gödel himself, not a man given to effusive praise, wrote to Cohen after reading his proof and said that reading it had given him the same pleasant effect as seeing a really good play. Coming from Gödel, that is roughly equivalent to a standing ovation. But Gödel's own story is where the darkness of this subject becomes personal and unbearable. He was born in 1906 in Brno, in what was then Austria-Hungary. His family nicknamed him Herr Warum, Mr. Y, because he was relentlessly curious as a child. He proved his incompleteness theorems in 1931, at 25, demonstrating that any sufficiently powerful formal system contains truths it cannot prove. In 1938, he proved the consistency of the axiom of choice. His contributions to mathematics and logic are essentially without parallel. But after his friend, the philosopher Moritz Schlick, was murdered by a deranged student in 1936, Gödel developed an escalating paranoia, specifically a terror of being poisoned. He would eat only food prepared by his wife, Adele, a former nightclub dancer he had married over the objections of his family. At Princeton, his closest friend was Albert Einstein. The two walked home together from the Institute for Advanced Study almost every day, and Einstein reportedly told a colleague near the end of his life that he came to the Institute merely for the privilege of walking home with Gödel. In late 1977, Adele suffered a stroke and was hospitalized for an extended period. Without her to prepare his food, Gödel stopped eating. He was admitted to Princeton Hospital on December 29th, severely emaciated. He died On January 14th, 1978, he weighed 29 kilograms, 65 pounds. His death certificate reads malnutrition and inanition caused by personality disturbance. The man who proved that mathematics is consistent enough to include the axiom of choice starved himself to death because he could not trust the physical world to be safe. I do not know what to do with that fact. I do not think anyone does, but it lives in the same story as the axiom and the paradox, and I think it belongs here. But if the axiom of choice is optional, truly, provably optional, and Banach-Tarski depends entirely on it, then a question emerges that is much sharper than the philosophical debates of 1905. If the axiom is a choice, then the paradox is a consequence of that choice. And if the paradox is a consequence of a choice, then there must be a version of mathematics where the choice was made differently. A version where you cannot construct non-measurable sets. A version where every subset of three-dimensional space has a well-defined volume. A version where the Banach-Tarski paradox is simply, flatly false. That version exists. It was constructed in 1970, and the mathematical establishment, with full knowledge of its existence, decided not to use it. Before I get to that alternative universe, I need to tell you about the people who saw this coming, because there was a war, an actual, bitter, career-destroying war inside mathematics over exactly this issue, and the people who were on the right side of it lost. Luitzen Egbertus Jan Brouwer was born in 1881 in Overschie in the Netherlands. He was, by all accounts, a difficult man, brilliant, uncompromising, and possessed of a philosophical intensity that made his colleagues uncomfortable. His 1907 doctoral thesis has been described as the manifesto of an angry young man taking on the mathematical establishment on all fronts. And what Brouwer argued, almost 2 decades before Banach-Tarski was published, was that mainstream mathematics had made a catastrophic mistake. Brouwer's position, which he called Intuitionism, was radical in its simplicity. He said that mathematics is a mental construction. Mathematical objects exist only insofar as they can be explicitly built in the mind. If you cannot construct something, if you cannot exhibit it, if you cannot produce it step by step through a finite or constructively infinite process, then it does not exist. Period. This meant that the axiom of choice was not merely controversial. It was meaningless. The axiom asserts the existence of a function, the choice function, without providing any method for constructing it. In Brouwer's framework, such an assertion is not false. It is not even wrong. It is empty. It says nothing, because existence without construction is not existence at all. But Brouwer went further than just rejecting the axiom of choice. He rejected the law of excluded middle. For infinite sets, the law of excluded middle says that for any proposition P, either P is true or P is false. There is no third option. This seems as obvious as anything can seem. But Brouwer pointed out that for infinite sets, asserting that P is true or P is false amounts to claiming that we can, in principle, verify one of the two options. For finite sets, this is straightforward. Check every case. But for infinite sets, you cannot check every case. You would need an infinite procedure, and asserting that one of two outcomes must hold, without any way to determine which one, is, in Brouwer's view, a metaphysical claim disguised as a logical one. Without the law of excluded middle, huge portions of classical mathematics collapse. Proofs by contradiction which work by assuming P is false and deriving an absurdity, only prove that P is not false. In classical logic, not false equals true. In intuitionistic logic, not false is weaker than true. It means you have ruled out the negation, but you have not necessarily constructed a witness for the proposition itself. You know the treasure exists, but you have not found it. And for Brouwer, finding it was the whole point. David Hilbert, the most powerful mathematician in the world in the early 20th century, thought Brouwer was insane, not just wrong, but dangerous. Hilbert viewed intuitionism as an existential threat to mathematics. His famous retort has been quoted so many times it has become almost a cliché, but I will include it because it captures the fury of the conflict perfectly. Hilbert said that taking the principle of the excluded middle from the mathematician would be the same as prohibiting the astronomer, the telescope, or the boxer the use of his fists. Hilbert was not merely defending an intellectual position. He was defending a program. His dream, outlined in a series of lectures and papers beginning in the 1920s, was to place all of mathematics on a secure, formal foundation. He wanted to prove, using finite methods, that mathematics is consistent, that the axioms of set theory, including the axiom of choice, would never produce a contradiction. Brouwer's intuitionism was a direct attack on this program because it said the axioms themselves were illegitimate. You cannot secure foundations that should not have been laid. Gödel, of course, destroyed Hilbert's program in 1931 with the incompleteness theorems, proving that any sufficiently powerful consistent system contains truths it cannot prove and cannot prove its own consistency. But that is another story. What matters here is that Hilbert saw Brouwer not as a colleague with a different philosophical perspective, but as an enemy of mathematical progress, and he acted accordingly. This was not a polite disagreement between colleagues. This was war, and Hilbert fought it with institutional power, not just intellectual argument. In 1928, Hilbert had Brouwer expelled from the editorial board of Mathematische Annalen, one of the most prestigious journals in mathematics. The details are still disputed, but the essence is that Hilbert essentially gave the other editors an ultimatum. He could not coexist on the board with Brouwer. One of them had to go. Hilbert was Hilbert. Brouwer was removed. The effect was devastating. Brouwer had poured years of his life into developing intuitionism. He had built a framework. He had trained students. He had published extensively, and he was thrown out of one of the most important institutions in his field by dictatorial fiat. He largely abandoned his intuitionist program after the expulsion and withdrew into something approaching silence. The man who had been right, who had warned that non-constructive existence proofs would lead to paradoxes and pathologies, was destroyed for saying it. And here is the irony that I genuinely cannot get over. Brouwer's most famous result, the one that appears in every topology textbook, the theorem that bears his name and secures his place in the mathematical canon, is the Brouwer fixed point theorem. It states that any continuous function from a closed ball to itself has at least one fixed point, and the standard proof of this theorem is non-constructive. It proves the fixed point exists without showing you how to find it. It proves existence without construction. It does exactly the thing Brouwer spent his entire career arguing was illegitimate. The man who fought against non-constructive mathematics is remembered primarily for a non-constructive theorem. I spent about 3 hours trying to figure out if Brouwer himself ever commented on this irony. I could not find a definitive statement, but I find it hard to believe he did not notice. Now, I want to be very careful here, because it would be easy to tell this story as Brouwer was right and everyone else was wrong, and leave it at that. The reality is more complicated. Classical mathematics with the axiom of choice has been extraordinarily productive. It has generated results of breathtaking beauty and power. The Banach-Tarski paradox is disturbing, but the same framework produces the Hahn-Banach theorem, the spectral theorem, the Tikhonov theorem, results that are used every day in physics, engineering, and applied mathematics. Rejecting the axiom of choice to avoid Banach-Tarski is a bit like refusing to use electricity because it can also electrocute you. The tool is genuinely useful. The question is whether the cost of using it, the paradoxes and pathologies it brings, is a price worth paying. But what the constructivists understood, and what the mainstream was slower to appreciate, is that there is a deep connection between constructive mathematics and computation. This connection runs through something called the Curry-Howard correspondence, and it is one of the most beautiful ideas in all of mathematics. In 1934, Haskell Curry noticed a curious parallel between logical propositions and types in a programming language. In 1969, William Howard deepened this observation into a full correspondence, though his manuscript circulated only as Xeroxed copies until 1980. The correspondence says this: propositions are types, proofs are programs, and the process of simplifying a proof corresponds to the process of executing a program. A constructive proof of there exists an X with property P corresponds to a program that actually computes such an X. A constructive proof is, literally, an algorithm. Classical logic, with the law of excluded middle, does not have a clean computational interpretation. The law of excluded middle corresponds to a program that somehow already knows whether a proposition is true or false, without checking, which is not something a real computer can do. The axiom of choice corresponds to a program that makes uncountably many selections simultaneously with no rule, which is even further from anything a real computer can accomplish. Constructive mathematics, the kind Brouwer was fighting for, is the mathematics that has computational content. Every theorem is an algorithm. Every proof is a program you could, in principle, run. And in the decades since Brouwer's defeat, this has turned out to matter enormously. Modern proof assistants like Coq and Lean, the tools that are being used to formally verify mathematical proofs by computer, are built on constructive type theory, per Martin Loff's constructive type theory from the 1970s, and more recently, the homotopy type theory developed by Vladimir Voevodsky and others, starting around 2006, are active research programs that take Brouwer's ideas seriously as a foundation for all of mathematics. Brouwer was not a crank. He was not a fringe figure with a pet theory. He was a mathematician who saw, decades before anyone else, that the unconstrained use of non-constructive methods would lead to pathologies. He was proven right by Banach-Tarski, and he was destroyed by the establishment for saying so. You would think someone would have said something. Nobody did. At least, not loudly enough. The mathematical community accepted the axiom of choice, accepted its consequences, and moved on. Brouwer's Intuitionism was taught in philosophy of mathematics courses as a historical curiosity, not as a living alternative. And for most of the 20th century, that is where things stood. But there is another figure in this story who deserves attention. And his stand was not philosophical, but political. Ernst Zermelo, The man who introduced the axiom of choice in the first place had his own collision with institutional power. Zermelo was born in 1871 in Berlin. He formulated his axioms of set theory in 1908, creating the framework ZF that would become the foundation of modern mathematics. Abraham Frankl and Dorav Skolem refined the system in 1922, and John von Neumann added the axiom of foundation in 1925. The result was ZFC, the axiomatic system in which virtually all of contemporary mathematics is conducted. Zermelo's career was not easy. He suffered from tuberculosis. He resigned from the University of Zurich in 1916 for health reasons. He was rejected for positions at Breslau and Würzburg. He finally obtained a position at the University of Freiburg, where he worked until 1935. That year, the Nazi regime required all university employees to open their lectures with the Hitler salute. Zermelo refused. He wrote a letter of resignation rather than comply. It was a principled stand, and it cost him everything. He lost his position, his income, and his institutional affiliation. He was reinstated after the war, but by then he was old and broken. He died in 1953. So here is the scorecard. The man who introduced the axiom of choice lost his career for refusing to salute Hitler. The man who warned against the axiom's consequences was expelled from a journal by institutional fiat. The man who proved the axiom was consistent, starved himself to death from paranoia. The man who co-authored the paradox died at 53 after spending years feeding lice with his own blood to survive the Nazi occupation of Elwau. I need to tell you more about that last part, because it is one of the most extraordinary survival stories in the history of science, and it connects directly to the paradox in a way that I think is poetic and terrible. After Banach published the paradox in 1924, his career flourished in Elwau. By the early 1930s, he had become the gravitational center of one of the most remarkable mathematical communities that has ever existed. The Scottish cafe Kawiania Skoka was a coffee house in Elwau where Banach and his colleagues would gather, often for hours, to work on problems. Stanislaw Mazur, Stanislaw Ulam, Hugo Steinhaus, Mark Kak, Władysław Orlich. These were not just good mathematicians. Several of them would become among the most important mathematicians of the 20th century. Ulam would later work on the Manhattan Project. Kak would revolutionize probability theory, and they worked in a coffee house, scribbling proofs on marble tabletops that got wiped clean every morning by the waitstaff. Solutions were disappearing faster than they could be written. Finally, Banach's wife Lucia bought a large notebook and left it with the cafe's proprietor. Mathematicians who arrived at the Scottish cafe could request the notebook and add problems or solutions. This became the legendary Scottish book. 193 problems recorded between roughly 1935 and May 31st, 1941. For problem 153, Stanislaw Mazur offered a live goose as a prize for solving a question about the approximation property of Banach spaces. The problem waited 37 years. Per Enflo finally solved it in 1972, and Mazur, then elderly but still alive, kept his promise. In a nationally televised ceremony, he presented Enflo with a live goose. Mathematicians take their bets seriously. Then the war came and destroyed everything. The Soviet Union occupied Elwau from September 1939 to June 1941. Under Soviet rule, Banach was appointed Dean of the Mathematics and Physics faculty at Lwów University. The Soviets valued mathematicians, or at least they valued the prestige of having them. When the Germans took Lwów in June 1941, the occupation became lethal. In July, the Nazis executed a group of Lwów professors in what became known as the Massacre of Lwów Professors. Antony Lomnicki, who had supervised Banach's doctoral thesis, was shot. Włodzimierz Stozek, a close colleague, was killed. Hermann Auerbach, one of the Scottish cafe mathematicians, took his own life in the ghetto rather than face deportation. Julius Schauder, another member of the circle, was shot by a German patrol. Banach survived by working at Rudolf Weigel's Institute for Typhus and Virus Research. Weigel had developed a method for producing typhus vaccine that required human hosts to feed the lice used in the process. Small wooden boxes containing body lice were strapped to the feeder's legs. Each feeding session lasted 30 to 45 minutes while the lice gorged on blood. The lice were then infected with typhus bacteria and harvested for vaccine production. The work was revolting and dangerous, but it came with an Ausweis, an identity card that noted the bearer might be carrying typhus. The Gestapo generally avoided people with those cards. Weigel hired as many intellectuals, professors and resistance members as he could under the cover of his institute. It was, in a sense, a paradox of its own. Survival through parasitism, life sustained by the very creatures that could kill you. Wacław Cybulski, who worked at the institute, recalled the surreal atmosphere, world-class mathematicians debating functional analysis and measure theory, while lice fed on their blood. The mind creates mathematics under any conditions. The body is irrelevant to the proof. I have been obsessed with this topic since I was in university, and the thing that keeps pulling me back is not the mathematics. It is this: the human cost. Every major figure in this story paid a terrible price, and the mathematics they built, the theorems and axioms and proofs, survived them all. The Banach-Tarski paradox does not care that Banach is dead. It does not care that Tarski fled on the last ship. It does not care that Gödel starved. The mathematics is indifferent to the humans who created it. And that indifference is, in its own way, a foreshadow of the deepest implication of this entire story. That mathematics exists in a space that is not bound by human limitations, not bound by human mortality, and possibly not bound by physical reality either. But I am getting ahead of myself, because before we can confront that implication, I need to show you the alternative, the mathematical universe where none of this happens. The universe where every set has a volume, every piece of every sphere is measurable, and the Banach-Tarski paradox is simply, provably, false. It exists, it has a name, and the mathematical establishment chose, with full knowledge, not to live in it. In 1970, a mathematician named Robert Solovay, working at the University of California, Berkeley, published a paper in the Annals of Mathematics, volume 92, pages 1 through 56. The title was dry in the way that only mathematics papers can be. A model of set theory in which every set of reals is Lebesgue measurable, and the content was a quiet earthquake. What Solovay proved was this: if you start with the standard ZFC axioms and assume the existence of a particular kind of large cardinal, an inaccessible cardinal, you can construct a model of set theory where a weaker form of the axiom of choice holds, called dependent choice. But the full axiom of choice fails. And in that model, every set of real numbers is Lebesgue measurable. Every single one, no exceptions. Let me unpack what that means, because the implications are staggering. In the Solovay model, non-measurable sets do not exist. The Vitali set, the first example of a non-measurable set constructed by Giuseppe Vitali in 1905, the set that kicked off the entire theory of pathological subsets, cannot be built. The pieces in the Banach-Tarski decomposition cannot be constructed. And because those pieces cannot exist, the paradox disappears. You cannot cut a ball into 5 pieces and reassemble them into 2 balls, because the kinds of pieces you would need are not available. They are not hiding somewhere difficult. They simply do not exist in that mathematical universe. And here is the critical point that I think most popular treatments of this topic get wrong. The Solovay model is not a toy. It is not a weird edge case that mathematicians constructed as a curiosity. It retains dependent choice, which is a weakened form of AC that is strong enough to do most of the analysis that working mathematicians actually need. The Brouwer category theorem still holds. Countable unions of measurable sets are still measurable. Sequential arguments still work. You lose some things, yes. Tychonoff's theorem in its full generality fails. Not every vector space has a basis. At the mathematics that physicists and engineers actually use on a daily basis, most of it survives. Cohen himself suggested this line of investigation to Solovay. The man who proved the axiom of choice was independent, effectively said to his student, "Now go build the universe where it is false and see what happens." And what Solovay found was that a perfectly functional mathematics exists on the other side. The paradox is optional. I want to say that again because I think it is the most important sentence in this entire script. The paradox is optional. The thing that proves you can double a solid ball from 5 pieces, the result that contradicts every conservation law in physics, the theorem that has disturbed mathematicians for a century, is a consequence of a choice that could have been made differently. There is a consistent mathematical universe, studied and verified, and published in one of the most prestigious journals in mathematics, where it simply does not happen, where every set has a volume, where the pathological decompositions cannot be constructed, where the pieces that make Banach-Tarski work do not exist. And the mathematical establishment looked at this universe and decided to stay where they were. Interesting, but we will stay where we are. The convenience of the axiom of choice was worth the paradox it produces. But the Solovay model has a price, and the price is worth understanding because it tells you something about the structure of mathematical possibility itself. Solovay's construction requires the assumption that an inaccessible cardinal is consistent with ZFC. An inaccessible cardinal is a cardinal number so large that it cannot be reached from smaller cardinals by any of the standard set theoretic operations. You cannot get to it by taking power sets. You cannot get to it by taking unions. It sits above everything else, unreachable. The existence of such a cardinal cannot be proved from ZFC alone. It is, in a sense, an axiom on top of axioms, a further assumption about the largeness of the mathematical universe. In 1984, Saharan Sheila proved that this assumption is necessary. You cannot get Solovay's result without it. The inaccessible cardinal is not a convenience, it is a requirement. So the universe where every set is measurable and Banach-Tarski disappears exists, but only if you are willing to assume that the mathematical universe is large enough to contain an inaccessible cardinal. Pay attention to this next detail, because it explains something fundamental about what mathematics is. The Solovay model says that if you accept a certain kind of mathematical largeness, an inaccessible cardinal, you can reject the axiom of choice and get a universe with no paradoxes, no pathological sets, no non-measurable monsters. But if you accept the axiom of choice instead, you get a universe that is in some ways richer, with more theorems, more structure, more power, and also more paradoxes. The choice between these two universes is exactly that, a choice, not a discovery, not a deduction, a decision about which mathematics you want to inhabit. And mathematicians overwhelmingly chose the universe with the paradox, because the axiom of choice was too useful to give up. Too many theorems depended on it. Too many tools required it. The convenience outweighed the discomfort, and the Solovay model was filed away as a technical curiosity, studied by logicians and set theorists, but not adopted as the working foundation of mathematics. People thought they had the full picture. They were wrong, because the Banach-Tarski paradox is not just about axioms. It is also about dimensions. And the dimensional aspect of the story reveals something that I think is far more unsettling than the axiomatic debate. I mentioned earlier that the paradox works in 3 dimensions, but not in 1 or 2. Now I need to explain why. Because the reason goes straight to the heart of what makes 3-dimensional space special. In 1923, the year before the Banach-Tarski paper, Banach himself proved something remarkable. He showed that in 1-dimensional and 2-dimensional Euclidean space, there exists a finitely additive isometry invariant measure defined on all subsets. Every subset of the line has a length. Every subset of the plane has an area. Not in the Lebesgue sense, which only covers measurable sets, but in a weaker sense that still prevents paradoxical decompositions. This Banach measure directly implies that you cannot decompose a planar region into finitely many pieces and reassemble them into a larger region. Banach-Tarski is impossible in 2 dimensions. The reason comes down to a single algebraic fact. The rotation group in 2 dimensions, SO2, is abelian. Every pair of plane rotations commutes. Rotate a disk by 30 degrees and then by 45 degrees, and you get the same result as rotating by 45 degrees first and then by 30. This commutativity means you cannot generate a free group inside SO2, and the free group is the engine of the entire paradox. Without it, the algebraic trick that lets you decompose a group into pieces that reassemble into 2 copies of itself simply cannot start. In 3 dimensions, rotations do not commute. The rotation group, SO3, is non-abelian, and crucially, it contains a free subgroup isomorphic to F2. The 2 rotations I described earlier, by the angle whose cosine is 1/3 around the x-axis and z-axis, generate this free subgroup. The non-commutativity of 3-dimensional rotations creates enough algebraic structure for the paradox to take hold. John von Neumann recognized this in 1929. In a paper published in Fundamenta Mathematicae, Volume 13, pages 73 through 116, he introduced the concept of amenable groups. An amenable group is one that admits a finitely additive, left-invariant probability measure on all its subsets. Roughly speaking, amenable groups are the well-behaved ones, the ones where paradoxical decompositions cannot happen. Von Neumann proved the dichotomy. A group admits a paradoxical decomposition if and only if it is non-amenable. And the key fact is that the Euclidean group in 1 and 2 dimensions is solvable, hence amenable, while in 3 dimensions it contains a free subgroup and is therefore non-amenable. The English term amenable was coined by Malandé in 1957, and it is a pun. The word means both well-behaved and meanable, capable of supporting a mean, which is to say a finitely additive invariant measure. It is one of the better jokes in mathematical nomenclature, and mathematical nomenclature is not known for its comedy. So, here is the picture. In 1 and 2 dimensions, the geometry is too simple for the paradox. Every set can be measured. The rotation groups are abelian. Everything is amenable. In 3 dimensions, the geometry becomes complex enough. The rotation group becomes non-abelian enough that a free group can form inside it, and the paradox becomes possible. You live in 3 dimensions. The space you occupy, the space your body takes up, the space through which light travels to your eyes is exactly the dimensionality where the Banach-Tarski paradox works. Not 2, not 1, 3. The universe did not have to be 3-dimensional. String theory suggests there may be 10 or 11 dimensions compactified in ways we cannot perceive, but the large-scale spatial dimensions you experience, the ones you move through and measure and build in, are 3. And 3 is the threshold. I do not know what to make of that. I do not think anyone does. But the fact that the paradox becomes possible, precisely in the dimensionality of the space we inhabit, feels like it should mean something. Whether it actually does is a question I cannot answer, but it sits there, uncomfortable and unresolved. Now, there is one more piece of the story I have been saving, because it complicates the narrative in a way that I think is important. The Banach-Tarski paradox uses non-measurable pieces. The axiom of choice is needed to construct those pieces. In the Solovay model, the pieces cannot exist. This is all true, but in 2017, something happened that scrambled the boundary between constructive and non-constructive mathematics. The problem is called Tarski's circle squaring problem. Tarski himself posed it in 1925, the year after the paradox paper. He asked whether a disk in the plane can be cut into finitely many pieces and reassembled into a square of equal area. Note the critical difference from Banach-Tarski. Here the area is the same before and after. We are not doubling anything. We are just rearranging. In 1990, Miklos Lachkovich solved the problem affirmatively. He showed that a disk can be decomposed into roughly 10 to the 50th power pieces and reassembled into a square of equal area using translations alone. But his pieces were non-measurable. They required the axiom of choice. Then in 2017, Andrew Marks and Spencer Unger, working at UCLA and Northwestern respectively, published a paper in the Annals of Mathematics, volume 186, pages 581 through 605. That gave a completely constructive solution. Their pieces were Borel sets, sets that can be built from open sets using countable operations, the most well-behaved sets in all of analysis. No axiom of choice needed. No non-measurable pathology. A clean, constructive, computable decomposition of a disk into a square. This result does not resolve the Banach-Tarski situation, because the Banach-Tarski paradox involves doubling volume, which is impossible with measurable pieces. But it shows that the boundary between what requires AC and what does not is still moving. mathematics is still figuring out which results genuinely need the axiom of choice and which merely used it as a shortcut. And every time a result that was thought to require AC is proved constructively, the case for the axiom weakens slightly. The territory that AC controls is shrinking, slowly but measurably, if you will forgive the expression. But this brings us to the question that has been underneath this entire story. The question I have been building towards since the opening. The one that Banach and Tarski did not answer, that Gödel and Cohen did not answer, that Solovay did not answer, that Brouwer fought his entire career to force people to confront. The question that sits at the bottom of the paradox, underneath the axioms, underneath the proofs, underneath the century of debate. If mathematics proves something that physics forbids, and both are internally valid, what does that tell you about the relationship between mathematics and physical reality? In 1960, the physicist Eugene Wigner published a paper in Communications in Pure and Applied Mathematics, Volume 13, pages 1 through 14. The title was The Unreasonable Effectiveness of Mathematics in the Natural Sciences, and it has haunted scientists and philosophers ever since. Wigner's observation was simple and devastating. Mathematics describes physics with an accuracy that has no right to exist. It is not just approximately useful. It is unreasonably, almost suspiciously precise. James Clerk Maxwell wrote down 4 equations in the 1860s that unified electricity and magnetism. And those equations predicted the existence of electromagnetic waves propagating at the speed of light. Maxwell did not discover radio waves in a laboratory. He discovered them in his mathematics, and then the mathematics turned out to be right. Radio waves were confirmed experimentally by Heinrich Hertz in 1887, 2 decades after the math predicted them. Paul Dirac wrote down an equation in 1928 that combined quantum mechanics with special relativity. And the equation had an extra solution that seemed to correspond to a particle with the mass of an electron, but a positive charge. Dirac initially tried to explain the solution away, but in 1932, Carl Anderson discovered the positron, a particle with exactly those properties. The mathematics predicted something physical that nobody was looking for, and it was real. Einstein published general relativity in 1915, and the equations predicted that massive objects would bend space-time, deflecting light that passed near them. Arthur Eddington confirmed gravitational lensing during the solar eclipse of 1919. A century later, in 2016, the LIGO collaboration detected gravitational waves, ripples in space-time that Einstein's equations had predicted 100 years earlier. The mathematics was not just ahead of experiment by years or decades. It was ahead by a century. Wigner wrote that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and that there is no rational explanation for it. He closed his paper by calling it a wonderful gift which we neither understand nor deserve. And here is where the Banach-Tarski paradox makes Wigner's observation intolerable. The same mathematical framework that predicted radio waves, positrons, and gravitational waves also proves that you can cut a ball into 5 pieces and build 2. The same axioms that underpin Maxwell's equations, Dirac's equation, and Einstein's field equations also produce non-measurable sets, paradoxical decompositions, and the duplication of solid objects through rearrangement, Physics and ball duplication come from the same source. They are consequences of the same axioms, and one matches reality with astonishing precision, while the other is physically impossible. If mathematics were simply a human invention, a tool we designed for our own convenience, then there would be no mystery. We built a tool. The tool has some useful features and some weird artifacts. The useful features help us do physics. The weird artifacts, like Banach-Tarski, are just bugs in the software. Discard them and move on. But Wigner's observation makes that explanation impossible to sustain. The effectiveness of mathematics is too precise, too specific, too unreasonably good to be an accident of human design. When a mathematical equation predicts the existence of a particle a century before it is discovered, that is not a tool behaving conveniently. That is something else, something deeper, something that suggests mathematics is touching a structure that exists independently of the humans who write the equations. And if mathematics is touching real structure, if it is discovering something rather than inventing it, then the Banach-Tarski paradox is also a discovery. The duplication of the ball is also real. In whatever sense, mathematical truth is real. And that means there is a level of reality where conservation of mass does not apply, where volume is not preserved, where a solid object can become two through rearrangement, a level that mathematics can access and physics cannot. This is the deepest implication. This is where it all converges. Mathematics is not the language of physics. That description is wrong, or at best, incomplete. Mathematics is larger than physics. It is a space of all logically consistent structures, and physical reality is one structure within that space. Physics lives inside mathematics the way a single country lives on a map of the world. There are vast mathematical territories that have no physical counterpart. Non-measurable sets, paradoxical decompositions, Banach spaces of arbitrary dimension, Hilbert spaces of uncountable dimension. Mathematics contains all of them, regardless of whether physics uses them or not. Let me be very precise about why the paradox cannot work physically. Because some people will hear, you can turn one sphere into two and wonder if there is some clever experiment that could make it happen. There is not, and the reasons are categorical, not just practical. Physical matter consists of a finite number of discrete atoms. A typical solid sphere might contain on the order of 10 to the 25th atoms. That is a large number, but it is finite. The mathematical ball in the Banach-Tarski theorem consists of uncountably many points, more points than there are natural numbers, more than there are atoms in the observable universe. The proof requires working with this uncountable infinity in ways that have no physical analog. You cannot cut a finite collection of atoms into non-measurable pieces, because non-measurable sets require infinite precision in their construction. Every physical cutting operation produces pieces with well-defined volumes. The pathological pieces in the theorem exist only in the mathematical continuum. Furthermore, quantum mechanics reinforces the impossibility. At the subatomic level, matter is quantized. You cannot divide an atom into pieces in the way the theorem requires. There is a minimum scale set by the Planck length, below which the concept of spatial position itself may lose meaning. The mathematical continuum, with its uncountable points and infinitely fine structure, may not correspond to the actual structure of physical space at all. Some physicists have pointed out that this is not a problem for physics. Physics does not claim that physical space is a mathematical continuum. Physics uses the continuum as a model. an approximation that works spectacularly well at the scales we care about. But the model is not the territory. The map is not the terrain. And the Banach-Tarski paradox lives in the map, not the terrain. But this is precisely what makes the situation so strange. If the continuum is just a model, if physical space is not actually made of uncountably many points, then why does the model work so well? Why do differential equations, which assume continuity, predict physical outcomes with 12 decimal places of accuracy? Why does general relativity, which treats space-time as a smooth, four-dimensional manifold, predict gravitational waves that LIGO detects exactly where and when the equations say they should appear? The model contains Banach-Tarski. The model also predicts reality with terrifying precision. It seems to be simultaneously wrong about what space is made of and right about how space behaves. I do not have a resolution for this. I do not think anyone does. But I want to map out the three main philosophical positions, because each one fails in a different way, and the way they fail tells you something about how deep this problem goes. The first position is mathematical Platonism. This is the view that mathematical objects exist independently of human minds. Numbers, sets, and geometric objects are real things, as real as chairs and electrons, just not physical. Gödel was a Platonist. On this view, the Banach-Tarski paradox describes something real. There really is a decomposition of a ball into 5 pieces that reassemble into 2. It just happens in a realm that is not bound by physical conservation laws. The problem with Platonism is that it cannot explain why some mathematical truths correspond to physics and others do not. If the mathematical realm is real and independent, why does physics get to pick and choose which parts of it apply? The second position is formalism. This is the view that mathematics is a game of symbol manipulation. Axioms are rules. Theorems are consequences of rules. There is no deeper meaning. The Banach-Tarski paradox is just what happens when you follow the rules of ZFC. It says nothing about reality because mathematics says nothing about reality. It is all syntax and no semantics. The problem with formalism is Wigner's observation. If mathematics is just a game, why does it describe physics so unreasonably well? Games do not predict the existence of particles. Games do not forecast gravitational waves a century in advance. Something more than symbol manipulation is going on. The third position is constructivism. This is Brouwer's view, updated for the 21st century. Mathematics is a human mental construction. Only constructive proofs have content. Non-constructive results, like Banach-Tarski, are not false. They are meaningless, artifacts of rules we should not have adopted. The problem with constructivism is that it restricts mathematics significantly, and some of the results it loses, like the Hahn-Banach theorem and Tychonoff's theorem, are genuinely useful in physics. Telling physicists they cannot use the axiom of choice is like telling engineers they cannot use steel. Theoretically principled, practically devastating. Each position explains part of the picture and fails on the rest. Platonism explains why math works in physics, but not why some math does not apply physically. Formalism explains why Banach-Tarski does not matter, but not why math predicts physics. Constructivism explains why Banach-Tarski should not have happened, but not how to replace the mathematical tools it would take away. The Banach-Tarski paradox sits at the intersection of all three failures, and the fact that no philosophical position can fully account for it suggests that we are missing something fundamental about the nature of mathematics itself. We have been treating mathematics as if it is a servant of physics, a tool for describing the physical world. But the Banach-Tarski paradox shows that it is more like a landscape that contains the physical world as one region among many. And we have been navigating that landscape using axioms, specifically the axiom of choice, that we chose for convenience rather than because we had any evidence they correspond to physical reality. A philosopher of mathematics named Joel David Hampkins at the University of Notre Dame has articulated a view he calls the set-theoretic multiverse. The idea is that there is no single correct set theory. There are many set-theoretic universes, each satisfying different axioms, each producing different mathematical truths. Some include the axiom of choice and have Banach-Tarski. Some include the Solovay model, where every set is measurable. Some satisfy the continuum hypothesis. Some deny it. They are all equally legitimate, connected by forcing extensions and large cardinal embeddings. If this view is correct, and it is taken seriously by a growing number of mathematicians and logicians, then the question, is the axiom of choice true, has no answer. Not because we have not figured it out yet, but because the question itself is malformed. It is like asking whether English is true. English is not true or false. It is a language. You can use it or not. The axiom of choice is a feature of some mathematical universes and absent from others. Whether the physical universe corresponds to a mathematical universe that includes AC or one that does not is an empirical question, and we have no way to test it. Think about what that means for physics. Every physical theory you have ever learned, every equation you have ever seen, every prediction that has ever been confirmed by experiment is formulated within a mathematical framework that includes the axiom of choice, the Schrödinger equation, Maxwell's equations, the standard model of particle physics, general relativity. All of them are expressed in mathematics that operates within ZFC. That means they all implicitly accept an axiom that cannot be proven true or false, and that produces, as a direct consequence, the ability to double a solid ball. Is the physical universe aware of the axiom of choice? Does the structure of space-time care whether you accept AC or reject it? Does the electron know which axioms were used to write the equation that describes it? These sound like silly questions, but they are exactly the questions that the Banach-Tarski paradox forces you to confront if you take it seriously. Because here is what keeps me up at night about this. The axiom of choice produces non-measurable sets. Non-measurable sets cannot be physically constructed. Therefore, in some sense, the mathematics that describes physics contains objects that physics cannot instantiate. The map contains territories that the terrain does not possess. And we have been using this map with spectacular success for centuries, navigating by it, building by it, predicting by it, without ever noticing that it contains regions that correspond to nothing in the physical world. What else is on the map that is not in the terrain? What other mathematical results have we been treating as descriptions of reality that are actually features of the mathematical landscape itself? Artifacts of the axioms we chose, with no physical counterpart at all? I do not know. And the unsettling thing is that I do not think there is a principled way to find out. Banach died on August 31st, 1945, at 53 years old, in Elwau, his body destroyed by wartime deprivation. In the final years of his life, while feeding lice at Rudolf Weigel's Institute to stay alive during the Nazi occupation, he continued to think about mathematics. Wacław Cybulski, who worked at the Institute, recalled that Banach and the other mathematicians discussed advanced problems while the lice gorged on their blood. The mind creates mathematics even when the body is being consumed. Colleagues who survived remembered that Banach seemed undiminished intellectually, even as he was visibly deteriorating. He was appointed to a chair at the Jagiellonian University after the Soviet reoccupation in 1944, but he never delivered a lecture. The lung cancer killed him before the academic year began. Tarski in Berkeley built one of the greatest logic programs in the world. He supervised 24 doctoral students, including Julia Robinson and Solomon Pfefferman. He made foundational contributions to model theory and formal semantics. Shortly after arriving in America, someone interrupted his seminar, claiming the work had already been done by Teitelbaum. Tarski, enraged by the implication of plagiarism, shouted, "I am Teitelbaum." He died in 1983. The Scottish book survived the war. Steinhaus rescued it from Elwau, and it was later edited and published. Problem 153, posed by Stanislaw Mazur, offered a live goose as a prize. It asked whether every Banach space with a Schauder basis has the approximation property. Per Enflo solved it in 1972, and Mazur, true to his word, presented Enflo with a live goose in a televised ceremony. The Banach-Tarski paradox survives everything. It survived its creators. It survived the war that destroyed the world they lived in. It survived the philosophical attacks of the Constructivists. It survived the existence of the Solovay model. It survived a century of discomfort, denial, and dismissal. It is still there, still proven, still true in the mathematical sense of true, which is the only sense in which it was ever claimed to be true. And the question is still open, the one that started this whole story. If mathematics proves something that physics forbids, and both proofs are valid, what is mathematics? What is it touching? What is the nature of the thing that can describe reality with terrifying precision and also contain results that reality forbids? You assumed, before you clicked on this, that math and physics were telling you the same story, that they were two languages for the same truth, that when math proved something, it constrained what physics could say. They are not telling you the same story. Mathematics is telling a bigger story. Physics is one chapter. And the chapter you are living in, the one governed by conservation laws and discrete atoms and measurable volumes, is not the only chapter in the book. There are other chapters. Chapters where a ball becomes two. Chapters where volume has no meaning. Chapters where the axiom of choice reaches into uncountably many collections and selects elements by a mechanism that no procedure could ever replicate. Those chapters are not speculation. They are proven. They are as mathematically certain as the Pythagorean theorem, and the axioms that produce them are the same axioms that produce the physics equations you learned in school. Here is something I keep coming back to. In 2005, a mathematician named Trevor Wilson published a paper in the Journal of Symbolic Logic, Volume 70, pages 946 through 952, resolving a question that had been open since Jan de Groot first posed it. Wilson proved that the pieces in the Banach-Tarski decomposition can be moved continuously into their new positions, not teleported, not magically rearranged, continuously translated and rotated through three-dimensional space, without any two pieces ever colliding during the process, from their original configuration into the configuration that forms two balls. Think about what that means. It is not just that the decomposition exists abstractly. The pieces can be physically moved, in the sense that continuous paths exist through space connecting the starting arrangement to the ending arrangement, with no overlaps at any point during the motion. The universe, if it contained non-measurable sets, would permit you to smoothly slide 5 pieces of a ball apart and together into 2 balls, like some nightmarish geometry puzzle that outputs more matter than it consumed. Of course, the universe does not contain non-measurable sets. At least, we do not think it does. We have no way to test whether it does. We just assume it does not, because the alternative is absurd. But mathematical absurdity and physical impossibility are not the same thing. The history of physics is littered with results that were dismissed as absurd until experiment proved them real. Quantum entanglement was absurd. Time dilation was absurd. The expanding universe was absurd. Each time, the mathematics said something the intuition rejected, and the mathematics turned out to be right. I am not saying Banach-Tarski will turn out to be physically real. I think it almost certainly will not. But I am saying that our confidence it is not physically real rests on physical assumptions about the discreteness of matter and the nature of space that are themselves unproven at the deepest level. We assume space is not a continuum. We assume matter is discrete. We assume non-measurable sets have no physical existence. These are reasonable assumptions. They are not proven facts. And the Banach-Tarski paradox is what you get when even one of those assumptions is wrong. The foundations of every scientific theory ever written rest on axioms that were chosen, not discovered. The axiom of choice was selected because it was useful, not because anyone proved it was true, not because anyone could. And the mathematics that follows from it says you can take a solid ball, cut it into 5 pieces, and build 2. Physics says you cannot. Let me end with the Scottish book. It survived the war. Steinhaus managed to rescue it from Elwau after the conflict. Years later, it was edited by R. Daniel Mauldin and published as a proper mathematical text. The problems inside it, scrawled in Banach's handwriting and in the hands of his colleagues, many of them dead by the time the book saw print, remain some of the most important, open, and solved problems in functional analysis. The goose for problem 153 was duly delivered. Per Enflo accepted it with the seriousness that the occasion demanded. But there is one detail about the Scottish book that stays with me more than any other. The mathematicians wrote in it at a cafe. They drank coffee. They argued. They scribbled proofs on marble tables and then, when the proofs were good enough, transferred them to the notebook. The problems in the Scottish book were not created in offices or libraries. They were created in a social space, in a place where people came to be together, where conversation and coffee and the warmth of a crowded room were part of the process. Mathematics, for all its abstraction, was done by human bodies sitting in chairs, brains fueled by caffeine and argument, hands holding pencils. The theorems are eternal. The people who created them were fragile, mortal, and subject to every cruelty the 20th century could inflict. Banach proved you can double a sphere. Then he fed lice with his blood to survive a genocide. Then he died at 53. The theorem does not care. It is still there. It will be there after everyone currently alive is gone. It was true before Banach was born. in the sense that the axioms that imply it have been consistent since before there were humans to write them down. The paradox exists in a space that is indifferent to human suffering, indifferent to human mortality, indifferent to whether anyone ever discovers it or not. Mathematics is larger than physics. It is larger than the universe, and the question of what it is made of, where it lives, is not a question that has ever been answered by anyone. Both are correct, and the question of which one is telling you the truth about the universe you live in is not a question mathematics can answer. It is not a question physics can answer. It is not a question that has ever been answered by anyone, and it may not be a question that has an answer at all.